The morning of March 23, 1945, near Dornot, Germany. A German tank commander stood in the turret of his Jagdtiger tank destroyer, watching through binoculars as American vehicles moved in the distance across a valley approximately 1,200 yards away. He was not concerned. His vehicle carried 180 millimeters of frontal armor, sloped at an angle that made it effectively thicker. The steel was face-hardened, produced in the factories of Essen with metallurgical precision that German engineers considered the finest in the world. He had been told, repeatedly, through technical briefings and tactical doctrine, that American guns could not penetrate this armor at combat ranges. The Americans had fielded their newest tank destroyers in recent weeks. Intelligence reports identified them as M36 Jacksons, mounting a 90mm gun. The German crews had discussed these vehicles with a mixture of curiosity and dismissal. 90 millimeters. The number itself seemed inadequate. German tank destroyers mounted 88mm guns, 128mm guns, and his own vehicle carried a massive 128mm PaK-44, capable of destroying any Allied tank at ranges exceeding 2 miles. The Americans, arriving late to armor development, were fielding a 90mm gun and expecting it to compete with German heavy armor that had been designed specifically to resist such weapons. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Jagdtiger commander had fought on the Eastern Front. He had seen Soviet 85mm guns bounce harmlessly off German armor. He had witnessed T-34 tanks destroyed at ranges where they could not effectively return fire. The technical superiority of German metallurgy and armor design was not propaganda. It was mathematical fact, confirmed through combat experience and proving ground tests. 180 millimeters of steel does not simply yield to conventional anti-tank weapons. The laws of physics, the calculations of kinetic energy and armor resistance were understood by both sides. German engineers had done the mathematics. At 1,000 yards, the penetration capability of a 90mm gun-firing standard armor-piercing ammunition was approximately 130 to 140 millimeters against vertical plate. The Jagdtiger's frontal armor, sloped and face-hardened, provided effective protection well beyond that threshold. Through his binoculars, the commander watched one of the American tank destroyers halt and traverse its turret. The movement was mechanical, precise, suggesting trained crews and quality equipment. The Americans were not incompetent. They had proven themselves capable in infantry operations, in logistics, in the overwhelming application of material resources. But armor design was a specialized field requiring metallurgical expertise, engineering sophistication, and industrial precision that took years to develop. Germany had been building heavy tanks since 1942. The Americans were newcomers to this particular contest. The gun fired. At this distance, over 1,000 yards, there was a delay between the muzzle flash and the sound of the shot arriving. The German commander saw the flash, a bright orange bloom in the grey morning light. Then came the sound, a sharp crack echoing across the valley. Then came the impact. The 90mm armor-piercing round struck the Jagdtiger's frontal armor at a velocity exceeding 2,700 feet per second. The round did not bounce. It did not shatter against the face-hardened steel. It did not create a shallow crater and fall away, as Soviet rounds so often had. It penetrated, completely. The round passed through 180 millimeters of sloped, hardened steel armor, as though the calculations, the metallurgy, the entire engineering philosophy behind German heavy armor design had suddenly become irrelevant. Inside the Jagdtiger, the crew experienced something that should not have been possible. German heavy armor doctrine in 1945 represented the culmination of years of armored warfare evolution. The philosophy had begun in earnest after the Battle of Kursk in July 1943, where German forces committed over 2,000 tanks in the largest armoured engagement in history. The battle had revealed uncomfortable truths about the Panzer IV and earlier German tank designs. Soviet T-34 tanks and KV-1 heavy tanks had proven difficult to defeat with existing German weapons. The 88mm anti-aircraft gun, pressed into anti-tank service, had been effective, but it was a towed weapon vulnerable to artillery and requiring time to position. German tank designers received new specifications. Future tanks would mount heavy guns capable of defeating any Soviet armor at long range. They would carry armor thick enough to resist Soviet 85mm and 100mm guns at combat distances. They would represent technological superiority over numerically superior enemies. The Tiger I heavy tank, entering service in late 1942, carried 100mm of frontal armor and mounted an 88mm gun. It was formidable, respected by Allied tankers who faced it in North Africa, Italy, and Normandy. But German engineers were already working on something more capable. The Tiger II, called the Königstiger, or King Tiger, began production in January 1944. Its frontal armor measured 150mm on the turret face and 100mm on the hull, sloped at 50 degrees to provide effective protection equivalent to 180mm against anti-tank fire. The gun was the 88mm Quark 43 liters, 71, a longer, more powerful version of the 88mm gun that had proven so effective. This weapon could penetrate 132mm of armor at 2,000 yards using standard ammunition. The Jagdtiger represented the extreme evolution of this philosophy. Officially designated Panzerjäger Tiger Osv. B. It was built on the Tiger II chassis and carried a casemate superstructure housing the 128mm Pak 44 gun. The frontal armor was 250mm thick on the superstructure face. The vehicle weighed 75 tons, making it the heaviest armoured fighting vehicle to see service during World War II. Only 79 were built between July 1944 and April 1945, but each represented German engineering at its most ambitious. The psychological impact of these vehicles on their crews was significant. Men, who had survived years of combat on the Eastern Front, who had seen friends die in burning T-34 seconds and Panzer IVs, now operated vehicles they believed were nearly invulnerable. German tank crews received extensive technical training. They learned the penetration tables for various weapons at different ranges. They understood that Soviet 85mm guns could not penetrate their frontal armor at ranges beyond 500 yards. They knew that American 75mm guns mounted on Sherman tanks were even less capable, requiring flanking shots or extremely close ranges to achieve penetration. This knowledge was not arrogance. It was engineering reality, confirmed through testing at the Kummersdorf proving grounds and through combat experience across multiple fronts. The armor protection was real, the guns were powerful. The vehicles, despite their weight and mechanical complexity, provided their crews with a level of protection unknown in lighter German tanks. The American 90mm gun began its development not as a tank weapon, but as an anti-aircraft gun. In 1940, as war in Europe demonstrated the importance of air defense, the United States Army Ordnance Department specified a new heavy anti-aircraft gun to supplement existing 3-inch weapons. The resulting 90mm M1 anti-aircraft gun entered service in 1941, designed to engage high-altitude bombers at ranges exceeding 10,000 yards. The gun fired a projectile weighing approximately 24 pounds at a muzzle velocity of 2,700 feet per second. It was heavy, requiring a fixed position or a substantial mobile mount, but it was effective against aircraft, and Army ordnance officers noted, theoretically capable as an anti-tank weapon. The North African campaign in 1942 and 1943 revealed American armor inadequacies. Sherman tanks with 75mm guns struggled against German Tiger tanks and Panther tanks with their sloped armor and powerful guns. American tank destroyers mounting 3-inch guns, later replaced by 76mm guns, achieved limited success. At the Tunisian Proving Grounds, and later at Aberdeen Proving Ground in Maryland, ordnance engineers began testing higher velocity weapons. The 90mm anti-aircraft gun, adapted for ground combat, showed promise. Tests conducted in 1943 demonstrated that the 90mm gun-firing armor-piercing ammunition could penetrate significantly more armor than the 76mm gun at equivalent ranges. Development accelerated. Engineers designed a modified version of the 90mm gun specifically for armored vehicle mounting. The gun retained the high muzzle velocity of the anti-aircraft version, but incorporated improvements for ground combat. The ammunition was refined. Standard armor-piercing rounds used in anti-aircraft applications were adequate, but ordnance engineers developed specialized armor-piercing capped rounds with improved penetration characteristics. The M82 armor-piercing projectile, weighing 24 pounds, achieved muzzle velocities of 2,700 feet per second. More significantly, development began on the T-30E16 armor-piercing projectile, incorporating tungsten carbide cores that dramatically improved penetration against face-hardened armor. The M36 tank destroyer, mounting the 90mm gun, entered combat in Europe in October 1944. Initial deployments were limited, with vehicles distributed to tank destroyer battalions supporting infantry and armored divisions. The crews trained on the weapon but lacked extensive combat data on its effectiveness against the heaviest German armor. Penetration tables provided to crews indicated the 90mm could defeat Tiger I frontal armor at approximately 800 yards and Tiger II side armor at similar ranges. Frontal engagements against Tiger II or Jagdtiger armor were considered inadvisable. The tables, based on standard ammunition and standard armor, did not account for the improved ammunition beginning to reach frontline units in early 1945. German intelligence officers, examining captured M36 vehicles in late 1944, assessed the 90mm gun as a moderate improvement over American 76mm weapons. Reports sent to German armored commanders indicated the gun posed a threat to medium German tanks, but was insufficient against heavy armor at typical combat ranges. These assessments were based on examination of the weapon itself and on knowledge of standard 90mm ammunition performance. The reports did not account for American metallurgical developments in ammunition design, specifically the incorporation of tungsten carbide penetrators that fundamentally altered the weapon's capabilities. By March 1945, when stocks of improved ammunition reached combat units in quantity, German armor doctrine had not been updated to reflect this new reality. The penetration of 180mm of armor at 1,000 yards was not an accident of luck or a statistical anomaly. It was the result of specific metallurgical and ballistic developments that had occurred in American ordnance laboratories during 1944. The key advancement was the T-30E16 armor-piercing projectile, later standardized as the M82 round with tungsten carbide core variants. Tungsten carbide, a compound of tungsten and carbon, possessed hardness characteristics that exceeded conventional hardened steel by substantial margins. When incorporated into an armor-piercing projectile as a penetrator core, tungsten carbide maintained its structural integrity under the extreme pressures of armor impact, allowing the projectile to punch through face-hardened steel that would shatter conventional steel penetrators. The physics of armor penetration depend on several factors. Kinetic energy, determined by projectile mass and velocity, provides the force. Projectile hardness determines whether the penetrator maintains integrity or shatters on impact. Armor hardness and thickness determine resistance. German face-hardened armor used a surface layer of extremely hard steel designed to shatter incoming projectiles, backed by softer, tougher steel to absorb remaining energy. This design was highly effective against conventional armor-piercing rounds. The hard face would crack the projectile, and the tough backing would stop the fragments. Tungsten carbide penetrators defeated this system by being harder than the face-hardened layer. Instead of shattering, the tungsten core maintained cohesion and drove through both the hard face and the backing plate. American ordnance engineers had been working on tungsten ammunition since 1943, initially for anti-tank rifle projectiles and later for larger caliber weapons. The challenge was manufacturing. Tungsten carbide could not simply be machined like steel. It required powder metallurgy processes, sintering at high temperatures, and precision grinding. Production capacity was limited by availability of tungsten ore, primarily imported from China and South America, and by the specialized facilities required for powder metallurgy. Initial production focused on smaller caliber ammunition. By late 1944, manufacturing capacity had expanded sufficiently to produce 90mm tungsten core projectiles in meaningful quantities. The projectiles began reaching combat units in January 1945, distributed first to units engaged in heavy combat, where encounters with German heavy armor were most likely. Tank destroyer battalions supporting armored divisions received priority allocation. The ammunition was not issued universally. Standard M82 armor-piercing rounds without tungsten cores remained the primary ammunition type, with tungsten core rounds allocated as special-purpose ammunition for use against heavy armor. Crews were briefed on the improved penetration characteristics, but lacked extensive field data. The penetration tables had not been fully updated. Crews knew the new ammunition was more effective. They did not yet know how much more effective. The muzzle velocity of 2,700 feet per second, combined with the 24-pound projectile mass, delivered approximately 160,000 foot-pounds of kinetic energy at the muzzle. At 1,000 yards, after air resistance reduced velocity to approximately 2,300 feet per second, the remaining kinetic energy was still sufficient to defeat heavy armor when combined with the tungsten carbide penetrator's superior hardness. German armor designers had calculated their protection requirements based on conventional steel projectiles. Their mathematics were correct for the threats they anticipated. The introduction of tungsten carbide penetrators changed the fundamental equation. The same kinetic energy, delivered by a harder penetrator that resisted shattering, achieved penetration that should have required substantially more energy with conventional ammunition. German metallurgists understood tungsten carbide. German industry used tungsten carbide in cutting tools and dies. The material properties were well documented in German technical literature. What German intelligence had failed to communicate effectively to armored units was that the Americans had successfully incorporated tungsten carbide into armor-piercing ammunition for 90mm guns and were manufacturing such ammunition in quantities sufficient for battlefield use. Intelligence reports from late 1944 mentioned American experimentation with tungsten ammunition, but characterized it as limited in scope and availability. By March 1945, this assessment was dangerously outdated. American production of tungsten core ammunition had reached levels where tank destroyer battalions could expect regular resupply. The gap between German intelligence assessments and battlefield reality was about to produce devastating consequences for German tank crews, who had based their tactical decisions on incomplete information. The engagement near Dornot involved elements of the 704th Tank Destroyer Battalion supporting the 80th Infantry Division's advance toward the Rhine River. The battalion had been in combat since Normandy, fighting through France and into Germany. They had engaged German armor repeatedly, primarily lighter Panzer IV tanks and assault guns that the 76mm guns on earlier American tank destroyers could defeat at reasonable ranges. In early March 1945, the battalion received M36 tank destroyers, mounting 90mm guns, replacing their older M10 tank destroyers. With the new vehicles came resupply of ammunition, including substantial quantities of the improved armor-piercing rounds with tungsten carbide cores. The crews trained briefly on the new vehicles and weapons. Gunnery practice at ranges behind the front lines familiarized them with the weapon's characteristics. The 90mm gun had more recoil than the 76mm gun they were accustomed to, requiring adjustments in firing technique. The improved penetration characteristics were explained in technical terms. but the crews lacked combat experience with the weapon against heavy German armour. On March 22nd, intelligence reports indicated German heavy armour in the sector. Prisoners from the 653rd Heavy Panzerjäger Battalion confirmed that Jagdtiger tank destroyers were operating in the area. American commanders issued warnings. The Jagdtiger's armour was known to be extremely heavy. Frontal engagement was considered dangerous, even with the 90mm gun. The morning of March 23rd brought overcast skies and poor visibility. American infantry advancing toward Dornot encountered resistance from German positions on high ground overlooking the approach routes. Artillery support was called, but German armour was reported moving to support their infantry. Tank destroyers from the 704th Battalion moved forward to positions where they could provide overwatch for the infantry advance. Crews scanned the terrain through binoculars and telescopic sights, searching for German armour. At approximately 0830 hours, a crew commanded by Staff Sergeant Robert Early identified a German vehicle at extreme range, estimated at 1,200 yards. The vehicle was partially hull down behind a low ridge, exposing only its superstructure. Through the gun sight's magnification, the distinctive profile of a Jagdtiger was identifiable. Staff Sergeant Early faced a tactical dilemma. Standing doctrine advised against frontal engagement with Jagdtiger armour at ranges beyond 500 yards. The penetration tables provided with standard ammunition indicated insufficient penetration capability at the current range. However, the crew had been briefed that their tungsten core ammunition provided substantially improved performance. Early made the decision to engage. His gunner, Corporal James Mitchell, loaded a tungsten core armour-piercing round. The gun was laid on target, adjusting for range and the slight crosswind. The reticle in the gun sight was positioned on the visible portion of the Jagdtiger's superstructure, aiming for the centre mass of the frontal armour. At 0833 hours, Mitchell fired. The 90mm gun recoiled violently. The muzzle blast threw dust and debris from around the tank destroyer's position. Through the gun sight, as the vehicle settled back from recoil, the crew observed the impact. The armour-piercing round struck the Jagdtiger's frontal superstructure slightly left of centre. There was a bright flash of impact, a shower of sparks, and then, critically, no ricochet. The round had not bounced off at an angle as rounds striking heavy armour typically did. Seconds later, smoke began pouring from the Jagdtiger. Not engine smoke from the rear deck, but thick, dark smoke from the crew compartment, indicating internal fire. The Jagdtiger remained stationary. Its gun did not traverse toward the American position. No return fire came. Within minutes, crew members were visible evacuating the vehicle, 3 men scrambling from hatches and moving away from their burning vehicle. Staff Sergeant Early and his crew stared in stunned silence. They had just achieved a frontal penetration of what was supposed to be the most heavily armoured vehicle in the German arsenal at a range exceeding 1,000 yards. The technical impossibility of what they had witnessed created cognitive dissonance. Their training said this should not work. Their penetration tables, based on standard ammunition, indicated insufficient capability. Yet the evidence was undeniable. The Jagdtiger was burning. Its crew had abandoned it. A single round from their 90mm gun had achieved what German armour doctrine said was impossible. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The engagement was reported up the chain of command within hours. Other crews in the battalion received word that a Jagdtiger had been knocked out at long range by frontal shot. Skepticism was the initial response. Requests for confirmation came back. Staff Sergeant Early's crew provided detailed account of the engagement, including range estimation, point of impact, and observed results. After-action reports compiled over the following days would document this engagement and several others like it. The 90mm gun with tungsten core ammunition was proving far more capable than initial assessments had indicated. For the German crew of the destroyed Jagdtiger, the experience was fundamentally disorienting. The commander, Oberfeldwebel Klaus Bäumer, a veteran of the Eastern Front with 3 years of combat experience, had operated under specific tactical assumptions. Those assumptions were based on engineering data, on tested performance of German armor against known threats, on the proven resistance of face-hardened steel armor to conventional anti-tank weapons. The Jagdtiger's 250mm frontal superstructure armor was not merely thick, it was considered effectively impenetrable to any weapon the Western Allies possessed at combat ranges beyond 500 yards. The sound of the impact was the first indication that something unexpected had occurred. Anti-tank rounds striking heavy armor typically produced a loud clang, a ringing impact as hardened steel met hardened steel. Rounds that failed to penetrate would ricochet away, often visible as they tumbled through the air. After deflection, the sound Bäumer heard was different. It was a sharp crack, followed immediately by a tearing, ripping sound as metal failed catastrophically. Inside the fighting compartment, the armor-piercing round had penetrated completely. The tungsten carbide core, traveling at over 2,000 feet per second even after crossing 1,000 yards of distance, punched through the face-hardened armor plate. Behind the plate was the crew compartment. The penetrating round, along with fragments of armor spalled from the interior surface, created a cone of lethal fragments traveling at supersonic velocity. The loader, standing near the ammunition racks, was struck by multiple fragments. He was killed instantly. The gunner, seated at the gun controls, was wounded by fragments that struck his left side and arm. Bäumer, standing in the commander's position, felt the shockwave of the penetration, the sudden overpressure as the round displaced air in the confined space. Fragments struck equipment, ricocheted off internal surfaces, and ignited stored ammunition propellant charges. Within seconds, fire spread through the fighting compartment. The driver, in the forward hull, was separated from the fighting compartment by an armoured bulkhead, but smoke began filling his position through ventilation ducts. Bäumer ordered evacuation. The wounded gunner needed assistance to exit through the side hatch. The driver abandoned his position and exited through the front hull hatch. Bäumer left last, after confirming the loader was beyond help. Outside the vehicle, lying in cover behind a low rise of ground, Bäumer experienced something beyond the immediate danger and loss. He experienced the collapse of a conceptual framework. His vehicle had been penetrated from the front at a range exceeding 1,000 yards by an American 90mm gun. This was not supposed to be possible. The technical data, the armor thickness, the calculations of effective protection, all indicated that such a penetration should require either much larger caliber weapons or much closer ranges. German intelligence briefings had characterized the American 90mm gun as a modest improvement over earlier American tank guns. Effective against medium armor, inadequate against heavy armor at typical combat ranges. The briefings were based on performance data for standard ammunition. What neither Bäumer nor German intelligence officers fully understood was that American ammunition had evolved beyond the standard steel projectiles used in earlier testing. The tungsten carbide core projectiles represented a qualitative change in penetration capability, not merely a quantitative improvement. German armor doctrine, developed over years of combat and engineering testing, had not accounted for this development. Over the following weeks, as more German heavy armor encountered American 90mm guns, the pattern repeated. Jagdtigers knocked out at ranges, previously considered safe. Tiger II tanks penetrated frontally by weapons that should have been ineffective. The psychological impact on German tank crews was severe. The protective advantage they had relied upon, the technological superiority that partially compensated for American numerical advantages, was eroding. Crews who had operated with confidence born from armor thickness now faced uncertainty. If American 90mm guns could penetrate Jagdtiger armor at 1,000 yards, what protection did any German vehicle offer? Tactical doctrine began changing informally among surviving German armor units. Crews avoided frontal engagements at all ranges with American tank destroyers mounting 90mm guns. Ambush tactics emphasized firing first from concealed positions, attempting to disable American vehicles before they could return fire. The days of German heavy tanks advancing confidently toward Allied positions, trusting in armor protection to survive initial enemy fire, were ending. By April 1945, as American and British forces advanced deeper into Germany, German armored units were fighting defensively, trading space for time, avoiding decisive engagement. The Jagdtiger, designed as a mobile fortress capable of stopping enemy armor advances through superior firepower and protection, had become a liability. Its 75-ton weight made it difficult to move, particularly as fuel supplies dwindled. Its armor, once considered its greatest asset, no longer provided reliable protection against weapons it was supposed to resist. The destruction of German heavy armor by American 90mm guns in March and April 1945 forced immediate tactical changes across German armored units. Reports from the 653rd Heavy Panzerjäger Battalion, which had lost multiple Jagdtigers to frontal penetrations, were distributed to other heavy armor units operating on the Western Front. The reports were stark in their assessment. American 90mm guns could defeat Jagdtiger frontal armor at ranges exceeding 1,000 yards. Tiger II tanks were similarly vulnerable. The armor protection that had been the foundation of German heavy tank doctrine no longer provided the security it had been designed to offer. German tank commanders issued new engagement protocols. Heavy armor would no longer advance toward American positions in daylight unless absolutely necessary for critical defensive operations. Engagement ranges were to be maximized, using the superior range of German guns to engage American armor before closing to ranges where American 90mm guns posed maximum threat. Ambush positions were to be carefully selected, providing concealment and cover, with retreat routes planned in advance. The emphasis shifted from armor protection to avoiding being hit at all. This represented a fundamental change in German armored warfare philosophy, acknowledging that protection through Christensen them, armor thickness was no longer sufficient. The tactical adaptations came too late, and with insufficient resources to matter strategically. By April 1945, German armored forces were scattered, under strength, and critically short of fuel. The Jagdtigers of the 653rd Heavy Panzerjäger Battalion, those that survived combat losses, were increasingly abandoned due to mechanical breakdowns that could not be repaired with available parts and tools. One Jagdtiger was found by American forces near Schwetzingen, abandoned intact with only minor mechanical problems that the crew lacked resources to repair. The vehicle was recovered and shipped to the United States for technical evaluation at Aberdeen Proving Ground. American ordnance engineers examined the armor carefully, noting the quality of the steel and the precision of the welding. They also examined penetration holes in recovered armor plates from destroyed vehicles, confirming that tungsten carbide core ammunition had achieved complete penetration through armor thicknesses exceeding 180 millimeters. The psychological toll on surviving German tank crews was documented through prisoner interrogations, conducted in April and May 1945. Crews expressed feelings of betrayal by their own high command, who had assured them their armor was sufficient. They described the terror of knowing that weapons previously considered inadequate could now kill them at ranges where they had felt safe. Some crews had refused to operate their vehicles in final defensive battles, abandoning them before combat commenced, recognizing that the vehicles offered insufficient protection to justify the risk. Oberfeldwebel Bäumer, captured in mid-April after his unit dissolved, told American interrogators that the penetration of his Jagdtiger had destroyed his faith in German engineering superiority. He had believed German technology was the best in the world. The reality that American ammunition development had rendered German armor doctrine obsolete was, in his words, more demoralizing than any battlefield defeat. American forces advancing through Germany in April 1945 encountered numerous abandoned German heavy armor vehicles. Jagdtigers, Tiger IIs, and other heavy tanks were found intact or partially destroyed by their own crews to prevent capture. Post-war analysis indicated that mechanical breakdown and fuel exhaustion caused more German heavy armor losses in the final months of the war than combat action. The vehicles that had been designed to provide mobile, protected firepower had become immobile fortresses, then abandoned hulks. The 704th Tank Destroyer Battalion, whose crew had achieved the documented long-range penetration of Tiger armor in March, continued operations through April until German surrender in May. Battalion records indicate they encountered decreasing resistance from German armor in final weeks of combat. German heavy tanks, when encountered, were typically in static defensive positions or already abandoned. The tactical dominance that American 90mm guns had achieved was rendered somewhat moot by the collapse of organized German resistance. The development of effective tungsten carbide ammunition for 90mm guns represented more than metallurgical advancement. It represented the full mobilization of American industrial and scientific resources towards solving specific military problems identified through combat experience. The process began with recognition that existing American anti-tank weapons were inadequate against German heavy armor encountered in Normandy during summer 1944. Reports from tank destroyer battalions and armored divisions indicated that 76mm guns struggled to penetrate Tiger and Panther tanks frontally. American tank crews were forced to flank German heavy armor, a dangerous and time-consuming tactic that increased American casualties. The War Department's response was systematic. Ordnance engineers at Aberdeen Proving Ground received priority tasking to develop improved ammunition for existing weapons and to accelerate development of larger caliber guns. The 90mm gun already existed in anti-aircraft form. Adapting it for anti-tank use required engineering work but not fundamental redesign. The ammunition development received particular focus. Metallurgists at the Watertown Arsenal in Massachusetts, working with industrial partners including Union Carbide and Kennametal Corporation, developed tungsten carbide core projectiles that could be manufactured at scale. The technical challenge was not creating hard penetrators. Tungsten carbide's properties were well understood. The challenge was manufacturing processes that could produce cores of sufficient quality and consistency in quantities measured in thousands of rounds per month. American industry's advantage was not merely size, but adaptability. Factories that had produced consumer goods before the war were retooled for military production. Companies with expertise in powder metallurgy, developed for peacetime applications like cutting tools and dies, applied that expertise to armor-piercing projectile cores. The learning curve was steep. Early production batches had quality control problems, with cores cracking during firing or failing to achieve expected penetration. By late 1944, manufacturing processes had been refined. Production capacity increased steadily through the winter. By March 1945, monthly production of 90mm tungsten core ammunition exceeded 15,000 rounds, sufficient to supply all tank destroyer battalions equipped with M36 vehicles, and to begin building reserve stocks. German industry, by contrast, was collapsing under the weight of Allied bombing, resource shortages, and transportation system destruction. German factories had technical knowledge equivalent to American facilities. German metallurgists understood tungsten carbide as well as their American counterparts. What German industry lacked by 1945 was production capacity, raw materials, and functioning infrastructure. Tungsten ore supplies, previously imported from Portugal and Spain, were interrupted by Allied naval blockade. Domestic German tungsten production from mines in Saxony was insufficient for all military and industrial needs. Priorities favored cutting tools for machine tools in aircraft factories rather than armor-piercing ammunition. Even if German ordnance departments had recognized the threat posed by American tungsten ammunition earlier, German industrial capacity to respond was limited. The asymmetry extended beyond ammunition to complete weapons systems. American production of M36 tank destroyers reached 1,413 vehicles by war's end. These were distributed across dozens of tank destroyer battalions operating in Europe and a smaller number in the Pacific theater. By comparison, Germany produced 79 Jagdtigers total. The Jagdtiger was arguably the more capable individual vehicle, with heavier armour and a more powerful gun. But industrial warfare between modern nations is not decided by individual vehicle capabilities. It is decided by production capacity, by the ability to field sufficient quantities of adequate equipment, by logistics systems that keep vehicles supplied and maintained, and by the flexibility to adapt to changing battlefield conditions. American military doctrine emphasized standardization and mass production of adequate equipment over perfection. The Sherman tank was not the best tank of World War II in any technical category. It was outgunned by German Panthers and Tigers. It had less armour than comparable Soviet tanks, but it was reliable, easy to maintain, and produced in quantities that ensured American armoured units always had operational vehicles. The 90mm gun mounted on M36 tank destroyers followed the same philosophy. It was not the largest gun that could have been designed. It was the largest gun that could be reliably mounted on available chassis, supplied with ammunition in necessary quantities, and fielded in time frame that mattered for the war effort. This pragmatic approach, combined with American industrial capacity, produced weapons systems that were sufficient to defeat German heavy armour when it mattered most. The encounters between American 90mm guns and German heavy armour in spring 1945 illustrated principles of industrial warfare that extended far beyond the specific technical matchup. German heavy armour doctrine was based on sound engineering principles. Thick, face-hardened armour did provide excellent protection against conventional anti-tank weapons. German guns were powerful and accurate. German crews were well-trained and experienced. None of these advantages proved sufficient when confronted with an adversary capable of rapidly developing and deploying counter-technologies at industrial scale. The tungsten carbide ammunition that defeated German armour was not German engineering failure. It was American industrial adaptability, achieving practical results faster than German intelligence could assess the threat and German industry could respond. The psychological dimension was as significant as the technical. German tank crews in March 1945, who climbed into Jagdtigers and Tiger IIs, did so with belief systems shaped by years of technical superiority. They had fought on the Eastern Front, where German guns outranged Soviet tanks and German armour resisted Soviet anti-tank weapons. They had received technical briefings explaining that their armour protection was calculated to resist known Allied weapons. The sudden revelation that these calculations were obsolete, that Allied weapons had evolved beyond German intelligence assessments, destroyed confidence in ways that affected combat effectiveness beyond the immediate tactical situation. Crews who no longer trusted their armour protection fought more cautiously, abandoned vehicles more readily, and suffered morale problems that compounded the material disadvantages Germany faced. American crews experienced the opposite psychological trajectory. The initial uncertainty about their 90mm guns' capability against heavy German armour gave way to confidence. Once combat results demonstrated effectiveness, tank destroyer crews who had approached encounters with Jagdtigers and Tiger IIs with appropriate caution in early March 1945 were engaging the same vehicles more aggressively by April, confident that their weapons could achieve penetration at combat ranges. This psychological shift translated into tactical aggressiveness that accelerated German armoured force collapse. The knowledge that German heavy armour could be defeated frontally at reasonable ranges meant American forces could advance more rapidly, with less concern about encountering heavy German tanks in blocking positions. The German tank commander who stood in his Jagdtiger turret that morning in March 1945, confident in his armour protection, watching American vehicles in the distance, represented more than an individual soldier facing combat. He represented a military and industrial system that had reached the limits of its capabilities. German engineering excellence, German crew training, German tactical doctrine, all were real and all were effective within their context. The context changed. American industrial capacity, American scientific research, American manufacturing flexibility produced weapons that German planning had not anticipated and German industry could not match. The 90mm armor-piercing round that penetrated 180mm of steel at 1,000 yards was not merely a technical achievement. It was proof that in industrial warfare between modern nations, the side that can adapt faster and produce at greater scale holds fundamental advantages that tactics and individual skill cannot overcome. The abandoned Jagdtigers and Tiger Ts that littered German roads in April and May 1945, some destroyed in combat, many simply left behind by crews who lacked fuel or faced mechanical problems they could not repair, were monuments to this reality. They were extraordinarily well-engineered vehicles. They were produced in insufficient numbers, supplied inadequately, and ultimately defeated not by superior enemy tanks, but by an industrial system that could identify problems, develop solutions, and implement them at scale faster than Germany could respond. The German crews who survived to become prisoners of war carried with them the memory of that moment when their confidence in armor protection died. The moment when machine gun fire or artillery convinced them to abandon vehicles they once trusted. The moment when their Jagdtiger, struck by an American 90mm round at what should have been a safe range, began burning from internal fire. The Americans who fired those shots, who witnessed German heavy armor burn and German crews evacuate, learned different lessons. They learned that industrial capacity matters, that the factories in Detroit and Pittsburgh and Cleveland were as important to victory as the actions of frontline troops. That technological adaptation, the ability to identify problems and solve them quickly, provided decisive advantages. That confidence, born from adequate equipment and abundant supplies, translated into combat effectiveness that courage and skill alone could not match. The story of German heavy armor in spring 1945 was the story of the war itself, told in miniature through the specific technical details of armor thickness and penetration capability and the specific human experiences of crews who trusted their equipment until that equipment failed them catastrophically. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.